when I was at Harvard, I was somehow got onto Avi Loeb's mailing list.
Okay.
Avi Loeb would send formal annual update about his accomplishments every year.
Oh.
Everybody on this mailing list.
Oh, that's lovely.
Yeah. How many papers he published, interviews, quoted in this, there, this, that, the other, funding he received, awards. Yeah. No, that's good to stay on top of all his stuff.
That's wonderful. I know another physicist who does something similar, but I won't say it now. Okay. It's basically 10 a.m. So I have the great honor of introducing Clay, who was our colloquium speaker yesterday. So Clay works on Stockman quantum field theory, and today he'll tell us about representation theory of solitons. Go for it.
All right, thanks, everybody. Everybody hear me? No mic needed? Yeah, okay. So I'm going to tell you about representation theory of solitons. Here are some real solitons. This talk is based on a smattering of 4 papers that I wrote last year with my 2 wonderful students and Kentaro Omori, who's faculty at University of Tokyo. So keep an eye out for my wonderful students. Diego will soon be a postdoc, and Nick will be on the market in a couple of years. Okay, so those of you who are at my colloquium, some of the motivation that I'll present now will be a little bit an echo of that, but it will help us warm up. It's very early in the morning for physicists. Okay, so we're going to come back to this scalar field theory in one space and one time dimension. We're going to be studying a Landau-Ginzburg theory to start. And this is the potential. So phi is our single real dynamical scalar field. And here's a potential. And what are you supposed to notice about this? So for now, in your mind, delete these terms. And then you have a monomial. So a potential with a definite scaling. And what that means is that if you flow to the infrared, this will hit some kind of critical point. In this case, I put phi to the 6th. If I had put phi to the 4th, that would have hit the critical Ising model if I kept the quadratic term tuned to 0. Here I put phi to the 6th, so I hit the next in the series of minimal models. I hit the tricritical Ising model, something with a few more relevant parameters. Yes?
And if you put phi squared?
If I put phi squared, it's gapped.
Then what?
Then it's gapped out. It flows to the empty theory in the long distances. Yeah. Okay, so that's what the leading term tells us. It tells us that that we're talking about some kind of critical point in the infrared. And then the subleading terms in the potential, you could think those are describing the relevant deformations of this critical point. And so here's some. You should not understand at all why I've turned on this funny combination. We'll come to understand that much later in the talk. Okay? But if you just accept for now, this is some relevant deformation in the language of the tricritical Ising model, that would be some combination of temperature and external magnetic field. That would be, so you can see from the shape of this potential that you get that you have a gapped theory at long distances, right? Because you just have 2 minima of the potential, and near each of them is a non-degenerate minima, looks quadratic. And so we have these two ground states or minima. We'll call them omega 1 and omega 2. And there doesn't seem to be any normal symmetry of this problem. For instance, there's no reflection symmetry about the origin. I put some odd terms in the potential. Okay, so the low energy physics here after turning on this deformation with lambda is gapped, and there are these 2 ground states.
But the minima are degenerate, right?
I have tuned it so that the minima are exactly degenerate. Yeah, exactly. Yeah, so we'll come to this. Yeah. Okay, so in that kind of physical situation where we have degenerate minima, we would like to understand what are the finite energy excitations of the system. Right? And we can distinguish 2 types of excitations. The first are what you might call particles. So kind of intuitively, a particle is a small excitation of this field phi above each vacuum. Okay? And we'll come to be more precise momentarily. So, you could think that you do some semi-classical quantization about the minima, you get some spectrum. Whether those are stable or not, you have to investigate in more detail. And the second kind of excitation that we'd like to talk about are solitons. Okay, so a soliton is where the field phi interpolates between these 2 degenerate vacua in space. So space, we're in one spatial dimension. Space is a line. So we look at x equals minus infinity. We happen to be in the ground state omega 1. And at x equals plus infinity, we're in the ground state omega 2. And we call that a soliton. Right? And one comment to keep in mind, something to think about, is that we always have to talk about these solitons. The minimum energy soliton in this kind of problem is stable. It cannot deform to a collection of particle excitations because there's kind of a topological stability here because the states are different. Okay, and this talk will be about symmetry. So we're going to try to understand particles and solitons and what we can say about their masses and multiplets and stuff like that. And so in general, you should expect whatever kind of notion of symmetry you have will organize these distinct kind of energy eigenstates into some kind of multiplets. And we're going to build upon that theme.
Sorry, Clay, I have a quick question.
Yeah.
So I just want to make sure, for example, for the solitons in the sine-Gordon model, you would call it particles instead of solitons, right?
Yes, I
In
think
your
I would call it
convention.
a particle. Yeah,
Okay, okay.
so there is a class of terminology here, but maybe it will be explained a little bit better, on the next slide. And you'll see why I make this distinction momentarily, but ask again if it doesn't become clear.
Sure, okay.
Okay. So let's be slightly more formal. Let's introduce some language to talk about this. So we quantize the theory on the real line. And the Hilbert space, which I call H, it breaks into different sectors. And these sectors are labeled by the boundary conditions of the theory at infinity. There's plus infinity and minus infinity. So they have a pair of labels. So we have these four sectors, H11, H22, H12, H21. Here at Hij, the field is in omega I at x is minus infinity and omega j at x is plus infinity. So what are these sectors of Hilbert space? These are what people would normally call super selection sectors. That's a fancy word. What it means is that when you act with a local operator on any of these sectors, you stay in that sector. The local operator cannot move you from sector to sector because for moving from sector to sector requires changing the behavior at infinity. You can't do that with any local disturbance. Yeah? So these are these super selection sectors. So these blue ones are the particles where the boundary conditions are the same at plus and minus infinity, and these purple ones, these are the soliton sectors. So that's an invariant way to distinguish what we're talking about. Okay, now let's bring in the story of symmetry here. So we're just talking about how does symmetry think about these decompositions. Well, we can distinguish two physical situations, one where symmetry is spontaneously broken, and one where it is not spontaneously broken. Yeah. So if a symmetry is spontaneously broken, it means it will move the vacuum state. Okay. So it's spontaneously broken, it will move you between these sectors somehow. Okay. If it is not spontaneously broken, it preserves the vacuum state, and so then it acts in a fixed sector. Now, something I'd like to emphasize before we continue is the standard normal global symmetries that we talk about in quantum field theory. And they have an interesting feature, which is that they always map in this terminology, they always map particles to particles and solitons to solitons, whether or not they are spontaneously broken. So for instance, if you have a Z2 symmetry that changes 1 to 2, if it acts on H11, it sends you to H22. So it keeps you in the concept of particles. Similarly, if it acts on H12, it would send you to H21. So it keeps you in the concept of solitons. So ordinary global symmetries always respect this total split into particles and solitons. They never mix them up. So what's our main question here that we're going to talk about? So I'm going to be telling you about some non-invertible or generalized global symmetries in these kinds of models. I'll introduce that concept as we go, but for now we just call this some global symmetry C, abstract notion. And our goal here to understand is what is the implication on the multiplets, what we're going to find. So what kind of representation theory governs the energy eigenstates when you have these generalized global symmetries. And more generally beyond that, you could ask what selection rules either on the S matrix or on correlation functions. Okay, so we want to answer all of these questions. So what are our main results? So we're going to describe the math that you need for this. There is some math, some medicine you have to take before you get to use it. And the kind of main punchline that you should remember is that when you have a non-invertible symmetry, you can have degeneracies that are qualitatively different from those invertible symmetries. In particular, you can have the mass of a particle being forced to be equal to the mass of a solid, the terminology that I was talking about. So non-invertible symmetry will not respect this particle-soliton distinction that I was making before. It will mix them up into the same multiple. Yeah.
Maybe trivial question. Mass of particle you define trivially because it is portionless or the energy profile is quadratic near the minima. How we define the mass of a solid?
Well, the Hamiltonian acts on each of these sectors and preserves the sector. So I feed literally the eigenvalue of the Hamiltonian. So for instance, in this kind of picture that we're all familiar with, just the eigenvalue of the Hamiltonian on the lowest energy state in that sector would be the lowest mass. And so some intuition about this kind of equality should be surprising. It suggests that these symmetries don't have a classical analog, right? There's a kind of good reason why ordinary symmetries keep particles and solitons split, which is that usually when you do semi-classical physics, you think of the quanta of the elementary field as light, and the mass of solitons, which come from semi-classical solutions to the equation of motion, you think of those as very heavy. So they're very far apart in those kind of calculations. They could never be degenerate. And here I'm saying we have some notion of symmetry, which forces them to be in the same multiplet. That means like an order 1 coupling is involved. Any questions? Okay, so then we're done with the motivation. Let's talk about what is non-invertible symmetry in a one space and one time dimension before we move on to studying how it gives us interesting multiplets. So this will be the math medicine I was talking about.
Just make sure you're going to go back to that example and tell us in detail how it works.
Yeah. Yeah, it's not just a motivating random sketch. It will be a real example again. Okay, so in non-invertible symmetry, what's going on? So how do you abstractly characterize it? You abstractly characterize it by saying that your theory has some topological line operators in it. Okay. That is supposed to generalize the notion of a symmetry charge that acts on a spatial slice and transforms the state. Okay. So these are like that. That's what these labels A, B, C, they'll label these operators that we have. Why topological? What does that mean? It means you can wiggle where you put them, and as long as you do small wiggles, nothing will change. Well, that means that they commute with the Hamiltonian, and more generally, they commute with the stress energy tensor. And so that's the conservation part. Okay? So this is the condition that kind of replaces the Noether's theorem. Now, what's special about these, or what's different than standard symmetries, is when we try to multiply them, we find some surprises. When we try to multiply them, so we take A and we multiply it with B, in general, we get a sum of other symmetry operators, but a sum, not a single unique one. If you have a standard group-like symmetry, if you multiply one group element times another group element, you get a unique third group element. That's one of the axioms of being a group. Here, we don't have that. So this is the generalization that we're doing. We just say we have some topological operators, so some operators that commute with the Hamiltonian, but their multiplication rule is richer. And you should be a bit skeptical that this is interesting, I think. And the way to convince yourself that it's interesting is to see that this actually happens in real examples. So real field theories that you wish to study just have this structure. So you don't have to look far. So for instance, the Landau-Ginzburg theories, tricritical Ising model, et cetera, they all have these kind of symmetries. And that's also true in higher dimensions. So you kind of forced to study this structure. Okay, so some technical details. So this label A, it indexes what you would call simple objects, simple lines, and it will have a finite range. So imagine there's some finite list of these topological operators. Oops, that was supposed to say analog of a finite symmetry. So this is like we're studying the analog of a finite symmetry group, not a continuous symmetry group. And we'll assume unitarity throughout. Okay, the next bit of mathematics that we need to know, which is not super important but good to keep in mind, is that the structure of these lines, these A, B, C, etc., it has more than just a multiplication rule. It has, it has like a 6J symbol if you want to think in group theory terms. So, meaning you can look at how they fuse in different orders. And there's some consistency condition, some kind of a state of consistency condition here. And more technically, what that does is it converts this symmetry into what's mathematically known as a fusion category. So this is the setting, the mathematical setting where this symmetry lives. So I said that our symmetries no longer form a group. You could ask, well, what structure do they form? They form what is called a fusion category. So that's the algebraic setting. Studying these.
What's the meaning of the line with the arrow?
The line is the topological line that I'm talking about. So in general, they are oriented. They have an arrow on them. If you have in the group-like case, the arrow is just switching the arrow changes G to G inverse. In the non-group-like case, switching the arrow means conjugate it with CPT. So it's kind of like basically try to take the dagger of it. And unitarity tells us that in any QFT, whenever you have an operator, you have a dagger of this operator.
So just to make sure I understand the dimension counting. So in usual 3 plus 1D, a standard symmetry you said corresponds to like a 3D spatial slice.
Yeah.
And so like a one-form symmetry would be a 2-dimensional slice. So now in 1 plus 1D, a standard symmetry is a 1D line.
Yep.
And your like one-form symmetries are now going to be points.
Yeah, but we have no one-form symmetries in this discussion.
Oh, okay. This is all just going to be 0.
The generalization that I'm doing here is not changing the dimension. So the dimension of my operators is the same as for ordinary symmetries. The generalization that I'm doing is here, that I permit a more radical algebraic structure.
Okay.
Okay, so let's try to flesh out this this discussion a little bit. So in a relativistic theory, I'll mostly be in relativistic theories here. Every extended operator defines a defect. This is an interesting point. So if you have something that can act on a spatial slice, you can also rotate it 90 degrees and think of it as hitting a point in space and extending in time. That's a defect in your system. Okay. So operators act on the Hilbert space at fixed time. Defects create local modifications of the Hilbert space. And so this means that for each symmetry operator that I was talking about, we'll also have a defect in our system, a potential defect. Okay? So this produces what we call a defect Hilbert space. If you quantize the theory where the line A extends in time, that's the defect Hilbert space HA. And you could ask, what is that? How do you think about it in terms of operators? What are the elements of this Hilbert space? Well, one way to think about it is in terms of the state operator correspondence. In that case, what this HA describes is what is commonly called twisted sector operators. So the red is like a local operator, except for it's not quite local. It has this topological line coming out of it. So people have studied these a lot, actually, throughout the history of QFT. They just maybe didn't use this language. So you study correlation functions. Maybe you find that the correlation function is not single valued. It has a branch cut. How should you interpret that? One way to interpret it is that the branch cut means that there's a topological operator there. And so this is actually quite a familiar thing to do in QFT.
Do you have in mind the same branch cut that, like, if you have a gap and then the clean function has a cut in front of the gap,
exactly.
So it's like the same cut?
Yeah.
Cut.
Yeah, exactly. If the correlation function of your operators is not single valued, then you can always interpret it as saying that the operator that you were studying was really not an exactly genuine local operator, but was in a twisted sector. So it's kind of language for dealing with actually quite a familiar situation in field theory. Even with free fermions, we discussed, or free bosons, we encountered this sort of thing.
So kind of a terminological question. Normally, I think of, when I say Hilbert space, I think of it sort of as including the defect Hilbert space. Are you separating these two?
I mean, so imagine you quantize, you have one spatial dimension. Imagine you quantize on a circle. If you quantize on a circle with no defects, this is the standard Hilbert space, and by the state operator map describes the local operators in the theory. Now we could say, no, I don't quantize on the circle. I put a defect at some point on the circle, and I quantize again. You could ask, what is the operator meaning of that? It's those operators.
But in general, in this talk, you're sort of separating the two. When you say defect Hilbert space, you're just
exactly. I'm thinking that the Hilbert space on a circle would decompose into sectors that we would keep track of separately. Okay, so as I said before, one of the main reasons that you have to think about this is just because it's there in real examples. So the one class of examples, very familiar examples, are one space and one time dimensional rational CFTs. So that includes Ising, tricritical Ising, etc., many others. Okay. These have these non-invertible topological lines with this fusion category symmetry. So that structure is there and has been known for a long time. And in fact, they have a very detailed understanding of them. So these topological lines, there's one for each primary operator, and we know their action on local operators looks like this. So you act with A on the state created by operator B, you get this formula where this factor here is computed in terms of the modular S matrix. So, these rational conformal field theories, they just have this structure built in. So that's one reason to study this. Okay, so we talked a little bit about the existence of these operators, these symmetries. We now have to grow up and start figuring out how do they act in different contexts. So our goal that we're trying to get to in the end is how they act on particles, solitons, some very physical question like that. A slightly easier question is how they act on operators. So one interesting thing about this symmetry is that the way it acts will depend on the spatial topology in your problem. So we're in one space dimension, so there are not many options. One option is that space is a circle. You have periodic boundary conditions. Another option is that space is an interval or a line. Well, that's the case we'll come to in a minute. But if space is a circle, you have this structure, which has been known for a little while, worked out by Okneanu. So the way it works is the fusion category. You want to know how it acts. So it acts by something called the tube algebra. So this diagram here, you should think that space is a circle, and then we have time going up. Okay? How does this element act? Well, this tube algebra, the elements of the algebra are these pictures here. It's a very graphical calculus. Okay? Elements are these pictures. So how do you think about this picture? So this is time, and this periodic direction is space. Okay, so to start with, we have A going up on the circle. So at a fixed time, we have this defect A. So that's this Hilbert space HA. And then C goes around the circle. It acts at a fixed time. And it takes you to HB. It outputs this B. And there's maybe some data at the junction that I'm expressing here. So this means that this Hilbert space, this C, can transform you from HA to HB. And there's a composition rule on these cylinders, which is really just a graphical calculus. So you just stack them. You want to compose them. So you compose them, and you do some manipulations to simplify these pictures and get another picture that looks like that. So that's what's called the tube algebra. It's a fancy way of saying that these symmetries, these non-invertible symmetries, act on the direct sum of these twisted sectors. They do not respect the decomposition. So for instance, they in general map local operators to twisted sector operators. And that's not something that happens for ordinary symmetries. So this is a bit of a mouthful, but you can take it as meaning that we know exactly how the symmetry acts on operators. So if the question was, how to deduce the consequences for operator spectra, we know the answer. We know all the representations, all the multiplets, all their fusions. So that part can take as known. And we're going to build on that. Any questions about this? It's a bit technical, but we're going to see some pictures like this in a minute.
The difference between the purple line and blue.
Purple line and blue line. This was just done here. I was trying to illustrate. They're both elements of C. I was just trying to illustrate that you take all these blue ones that appeared when you stack, and you can do a manipulation to make it look like the same thing, but with a new line in the middle. I mean, I've suppressed a lot of indices and sums there.
Sure, but in principle, they are.
It's all workoutable.
Same set of operators, just.
Exactly. Yeah. So what you will find is like you'll find a bunch of sums like this. Yeah. And it can be made extremely explicit what this is. I mean, this is just some very explicit finite matrix algebra that you can work out.
What is the relation between the statement that the algebra acts on the direct sum and this center of the category?
Yeah. So
it seems like they're supposed to be somehow related to each other from what you said. But...
Yeah. So I mean, I don't really want to derive this, but what this is saying is that if you wish to know, so the tube algebra acts on this direct sum, and you would like to decompose it into irreducible representations. Yeah. You'd like to know which are the basic units of representation, so you know what are the basic multiplets implied by this symmetry. And people have solved that question. I don't want to dwell on it too much. What it means is that the representations have this beautiful correspondence to the center of the fusion category, this Drinfeld center, which means that each simple object in the Drinfeld center labels one irreducible representation. And so there's this like really nice correspondence there.
Thank you. That's helpful.
Yeah.
So if I just, for example, take an invertible symmetry like electric charge, then operator is e to the I alpha q. The q is the charge. So the defect is just the twisting by phase.
Yeah.
When I go around the cylinder at kappa phase. And this so purple line is basically a product of two exponentials, which are denoted by these blue lines going in circles.
Yeah, in that case, it's invertible, so the composition would be really easy.
Yeah,
exactly. Yeah.
Right. Okay.
Yeah, but it's exactly what you're saying. Okay, so this fusion category symmetry that we're talking about, it acts in different ways depending on what space is. If space is a circle, we here have discussed in principle the answer to this question. And we're going to generalize that now. Okay. So all what I said before was basically known. Now we're getting into some new material. Okay. So we're going to consider the implication of this fusion category symmetry on manifolds with boundary. It's a fancy way of saying something very simple. We're in one spatial dimension, so the only manifold with boundary is an interval. Okay? So we're going to study our theory on an interval. So space is an interval. This, though, is a little bit subtle. There are different physical interpretations of this interval, depending on whether you're a condensed matter physicist or a high energy physicist. Okay? So one is the interval is just finite length. Interval means finite length interval. In that case, you have, for instance, a conformal system or other system on a finite interval with some explicit boundary conditions, and you wish to know the spectrum and the consequence of the symmetry. That's a very natural problem in condensed matter, for instance. Another possibility, which is closer to the particle physics motivation that I gave at the beginning, is that you think of the interval as really secretly infinite length. Okay? Why should I think of it as an interval? So if space is R, why should I think of it as an interval? Well, if you do really quantum field theory where space is non-compact, you need to put some boundary conditions at infinity to get finite energy states. Okay? So R, you should really think of as, there is some data at plus and minus infinity. And that data is some boundary condition, which secretly makes it into an interval. Yeah.
Doesn't it make it into a circle?
No, not necessarily.
Possibly into a circle with twisted boundary conditions? I'm kind of confused.
Well, the soliton sector, remember that super selection sector that we talked about. So they do not necessarily have to have the same boundary condition at plus and minus infinity.
But they're related, so they're typically they contribute to the twisted partition functions. So that's confused. That's like working on a circle with twisted boundary conditions. Isn't it?
Will it make a difference compared to what he's saying?
I'm not sure. I'm confused.
I think it's pretty much the same.
It might be the same.
Yeah, I'm confused about this.
Yeah.
Well, I would just say that if you're thinking that states on the real line are directly related to states on the circle in twisted sectors, the dictionary is more complicated than that. For instance, there's pairs of labels, and we're going to discuss how those pairs of labels, right? So the twisted sectors on the circle, their labels are by the symmetry elements themselves.
Yes.
The different sectors on the interval, their labels are by something else, which is related, but not exactly the same. Fishing out that distinction is coming.
Okay.
Yeah.
Can I ask a question about the finite interval? So this may be getting slightly afield, but say that I choose boundary conditions which are not consistent with conformal symmetry. Are there ever situations where I can do that and still preserve the non-invertible symmetry?
Yeah, definitely. Yeah.
What are the conditions for that?
Well, so I mean, it's a kind of bulk boundary OPE condition that you can work out. Yeah, we can talk about it, but yeah, it's definitely possible. Yeah.
So here you imply that you take some fixed space interval and study time evolution on that fixed interval. But if I take, like, for example, some worksheet of an open stream, you can have a hole in it, in the middle.
Yeah, you could do that too.
Like appear that's for some finite period.
You can do that too. We can be in a Euclidean signature and study some more complicated boundary conditions. Here but since my goal was to discuss implications on a Hilbert space, I've really very much restricted my two space-time dimensional theory to be time times something.
That's generalizable.
Yeah, generalizable. Yeah. Okay, so here is part of the answer to these questions. So what data do you need to know to think about this symmetry, this fusion category symmetry, in the presence of a boundary? Okay. So the data that you need is algebraically what's called a module category. That's a very fancy term. Let me unpack what that is. Okay. So what is this M? So M, it's a list of the possible boundary conditions. So you can think it itself contains some elements, little m, little n, etc. And it has bulk boundary fusion rules. Okay, so here is a boundary. So this gray will always mean sort of empty. The non-empty part is in between. So here's a boundary. It's M. A is one of these fusion category symmetries. You can act on it when it comes in and gives you N. That's also reflected in this kind of bulk boundary fusion rule. So you think that this fusion rule means this. So in more physics terminology, we would say that if this bulk symmetry line changes the boundary condition, then it's spontaneously broken. And if it preserves the boundary condition, then it is not spontaneously broken. This accounts for both possibilities. Okay? And I should say, since I said this is a modular category, there are also, just like I showed you some associators, some F symbols for the fusion category, there are some similar things, some bulk boundary associators that make this M into a modular category, not just a fusion ring.
Can I ask a question? So is this different than the way that these A lines are acting on the defects, or there's like some freedom of choice in how it's changing M to N?
Yes, so a given symmetry may admit different possible sets of boundary conditions on which it can act. Right? For instance, and which is relevant in your problem is a kind of dynamical question. So maybe if your symmetry is not spontaneously broken at all, in which case you should think there's one ground state and all the symmetries just act on this one ground state and keep it the same. Or maybe the symmetry is totally spontaneously broken, in which case it's sort of permuting all of them. Right? So that's which is realized in a given problem depends on energetics. We want a language that allows for both possibilities. Okay. So the second, so the So then we can ask, we're quantizing on an interval, whether finite or infinite length, what labels the super selection sectors? What are the sectors of Hilbert space that we need to talk about? And they are split into, their labels are pairs of elements in this module, right? So one boundary condition at plus infinity, one at minus infinity. Okay. So this is the answer to the question of what labels the sectors. It's not exactly the same. There is some relations, but it's not exactly the same. You need as when we had the circle. Okay, so this is the decomposition. So I showed you that motivating example where we had two states. We had H11, H22, H12, H21. Here, more generally, we have just these kind of sector decompositions. So you have, here's our interval, and you have boundary condition M on one side, N on one side. That's the sector. Okay.
So when you say that the symmetry is spontaneously broken, is there any analog of long-range order here? Like, is there some correlation function you can write down that?
If a symmetry is spontaneously broken, you will, in one space and one time dimension, you will expect a local operator order parameter that can distinguish the distinct ground states, right? So you'll have in this dimension, a TQFT is something rather simple. It consists of a bunch of topological local operators whose role in life is to distinguish these sectors.
Right.
Okay, so now we have this setup. We want to know, how does the symmetry act on this decomposition? Okay, so we're ready to say that. Okay. So we have our open spatial interval. Someone has told us this bulk symmetry C, and someone has told us what boundary conditions are. We want to know, how does the symmetry act? Well, it acts by something that we call the sphere algebra. Okay, so we introduce it this way. It depends on both the bulk symmetry and the boundary conditions. And the elements of this algebra are these pictures. Okay? So just like I had the tube algebra on a previous slide, where the elements of the algebra, you could think of them graphically as cylinders with some decorations. Here, the elements of the algebra are these decorated strips. Okay. How should you think about this? Yeah, go.
Yeah, sorry. The gray shading, because I thought, the gray shading was going to be the system of interest, and then it was going to be left boundary and right boundary. We've actually drawn it in the.
Sorry, I drew it the other way. Gray is empty. Nobody lives in gray. Yeah.
Okay, very good.
So the white here is where
that's your system.
That's my system.
Okay.
Yeah. So how should you think about this? So you have HMN to start with, that super selection sector, and then A acts. And it transforms it some way to HRS. Okay? And maybe there's some data at the junctions that I've suppressed. So first thing to notice is moving the super selection sectors in general. Okay? And composition is a similar graphical calculus. So you want to, this is space, this is time. So if you want to compose them, you just put them in time order. So here's a composition. And then you do some wiggles, you do some simplification, using all these associators, and you get a sum of other elements like this. So that's the composition rule.
Okay. So in this language, an invertible symmetry is one in which I combine A and B and I don't get a sum, I just get a single.
You'll get a single one, yeah.
Okay, and you had this statement early on that an invertible symmetry would only ever take me from H11 to H22. I can't go from like H11 to H12.
That's correct.
Is there a way of seeing that those statements are somehow equivalent in this picture?
Yeah, I mean, I need to tell you how we would have to also flesh out what invertibility means on the boundary conditions. But it just means that an invertible thing, when it acts on a boundary condition, it's either not spontaneously broken, so it preserves it exactly, or it's spontaneously broken, so it maps it to exactly one other thing. A non-invertible symmetry will have some amplitude to take you from one boundary condition to a sum of others. You have some channel for all of them.
Okay.
Yeah, so that's where that tricky part comes in.
It's more about what they're doing to the boundary,
that's
not
correct.
about how they're fusing.
Yeah, that's correct. Okay. All right, 1040. Okay, maybe I will go through this, but not in that much detail. So we want to do representation theory now. So we figured out what the algebra is. Right? We went through this long song and dance to figure out the algebra we want to do some representation theory of this algebra to figure out what are the implied multiplets. Okay. So you need to know the properties of this algebra and to know what you're talking about. I mean, we've exited the realm of group theory. So representation theory gets hard once you exit the realm of group theory. So this strip algebra is not too wild. It's an example in mathematics of what is called a C-star weak hop algebra. So it's an analog of what's called a group ring. You don't need to know too many details about this. You need to know why did this kind of structure occur? Well, in physics, when you talk about algebras that could be symmetries, especially in QFT, there are some notions that you need to make sense. It cannot be too wild. So one thing you need is that if you have a particle, there should always be an antiparticle. So if you have a representation R, there should be a notion of a dual representation. That's what that means algebraically. And if you have a one particle state, you should be able to make multi-particle states. And what that means is that there should be a notion of tensor product of representation. And actually this C-star weak hop algebra universe is exactly where those notions can be defined. So that's one way to see sort of why we landed there. This is a kind of matrix algebras where you can have duals and tensor products. So they have a potential good physical implication. And you can prove in general that that's the kind of algebra that you arrive at. Okay. In the interest of time, I'm going to skip this parts about that. Okay, so representations, we can also work out, so I promise I'm coming to the end of the math. We can also say, what are these representations? So we want to work out what are the representations so we know what the degeneracies are. And there is just like there was an abstract answer to what the representations were for this tube algebra, there turns out to be also a general answer to what the representations are for this strip algebra. Okay, it has a kind of fancy presentation in terms of a certain category of homomorphisms. But the punchline is that this is something computable, and each element of it corresponds to an era. Okay. How should you visualize these representations where they have a kind of very natural quiver diagram meaning, which is very useful for saying what they are. And these kind of quivers actually have appeared in the past. So how do you make a quiver? So you think of the nodes of the quiver are elements, are these ground states. And you're going to draw arrows. So a quiver means nodes and arrows, a directed graph. Okay? So we're going to have one node for each ground state, for each boundary condition. And then we draw arrows between these nodes. We draw one arrow. If they go between distinct nodes, think of that as a soliton. If they go from the same node to itself, that's a particle. So you can kind of visualize the representations this way. And I'll do that very soon. Okay, so maybe enough of the abstract nonsense. Let's go back to some real examples where we see this structure. Okay, so we're going to start with some integrable examples, some flows out of rational CFTs. Okay, so let's go to the tricritical Ising model. That's the first interesting example. So I flash here the CAC table for the tricritical Ising model. So what you need to know about this theory is that at the fixed point, there are the following interesting non-invertible symmetries. There is a Fibonacci symmetry. That's a line W that obeys W times W is 1 plus W. And there is also what is called the Tambara-Yamagami symmetry. The non-invertible fusion there is n times n is 1 plus eta, where eta is the Z2 invertible symmetry of the tricritical Ising model. So that's the symmetry of the system. We are going to break some of it because we're going to flow out of that. So not all of that symmetry will be there. So we're going to initiate an RG flow by adding a relevant local operator to the Lagrangian. And of course, the preserved symmetry depends on what you put there, that relevant operator. And you can work out the condition that you need for the symmetry to remain. And the punchline is that there are two interesting relevant deformations to study here. One of them preserves this Fibonacci symmetry, gives you a gap system with Fibonacci symmetry. And the other one preserves this Tambara-Yamagami symmetry, both of which are non-invertible. And so those are two different RG flows that we can initiate out of this system. And we're going to apply our representation theory machine now to determine the spectrum of finite energy states in those systems.
How do I interpret a gap state in 1 + 1p with Fibonacci symmetry? How do I interpret that gap state that has Fibonacci symmetry?
What do you mean by how do you interpret it?
Like normally, when I think about like theories which have this Fibonacci structure, I think of things like right equalizing, which are gapless, or more complicated types of CFTs that have Fibonacci fusion rules. I've never encountered a case where I have a gapped theory, which has.
Now you have.
What is it?
Well, it's a system with two ground states, and it has, this operator commutes with the Hamiltonian. I'll tell you what that implies about the spectrum. I'm kind of doing it for you right now. Okay, so we come full circle. We had this motivating example. Okay, so the O to 1 results in a gap theory with two vacua. And if you write it in the Landau-Ginzburg description, that's exactly what these coefficients and lower order deformations were. So I worked out for you that this is what it means to turn on O21. It means to perturb the highest order thing by this lower order combination. That can be worked out. So this theory has two ground states and corresponding at infrared, two topological local operators in the infrared. And the whole flow has Fibonacci fusion category symmetry. So we're going to see that spectrum, the consequences of that on the spectrum now. Okay, so you start working it out. So we have two boundary conditions. I called them omega-1 and omega-2 before, but it actually is more natural to label them as 1 and W, it turns out. And here are these bulk boundary junctions. So these are the boundary conditions, and these are the bulk fusion lines. And there are some junctions. And maybe there was a question before about how to see the non-invertibility here. You see that W, when it comes in and acts on a boundary condition, it can do a variety of interesting things, right? So it can take, for instance, W to 1, but it can also take this one to this one. So it's the fact that it has an amplitude to do both that's doing a lot of the work. Okay. And then there are these two interesting elements of the strip algebra. Remember, we're trying to study representations of the strip algebra. These are the two elements that you need to think about. So one of them is a map from a soliton sector to a particle sector, and the other is a map from a particle sector to a soliton sector. And these maps are not isomorphisms, but they do commute with the Hamiltonian. Okay, so let's say now, what is the representation theory finally? So the minimum energy state in this sector with distinct boundary conditions is a soliton, and it has some CPT conjugate, which is an anti-soliton going the other way. And this Fibonacci fusion symmetry maps these onto a non-zero state, ket P, in a particle sector. And so these states, soliton, anti-soliton, and particle, form a triplet of equal energy. So that's the representation, and that's the particle soliton degeneracy that I was talking about at the beginning. You can see the quiver that I was talking about associated to this representation. So we have two ground states. Think of these as nodes, and these arrows are telling us about the excitation. So there's a soliton going one way, a soliton going back, and a particle just over one of them. So that's the multiplet structure here. It's a very strange pattern of degeneracies, but it's what's implied by this Fibonacci symmetry. Okay. Now, symmetry alone cannot solve a quantum field theory, right? Symmetry does not, in general, predict the number of multiplets, right? If you have a SU2 symmetry of your problem, you know that states come in representations of SU2. You don't know in general how many. That's something you have to figure out some other means. Okay? So symmetry analysis alone does not predict the number of these triplets. It does tell us that there has to be one. And actually in this model, it's known that there's exactly one. People worked that out using the thermodynamic beta ansatz a long time ago. So in this case, there is this one. This model is integrable, so it's a good thing to benchmark your analysis. In the integrability discussion, the fact that the particle and soliton have equal mass is some kind of miracle. Here, it's just something that comes for free at the beginning because we just recognize the symmetry of the problem.
I thought I would expect two different local particles. You say one of them lives together with them because I have two degenerate vacua, right? And
you have two degenerate vacua?
Two local sets of.
No, the other one is unstable. The other one can decay.
Into
a soliton anti-soliton pair. That's highly non-obvious, but that's the result.
And this statement of this particle soliton has form a triplet. Does it have any dependence on the parameter lambda?
Good. So let's discuss that question afterwards. Actually, it's an interesting technical question. But yeah, let's come back to it. Okay, so one flow we solved, the one that preserves Fibonacci symmetry. Let me flash the answer to the other one. So I told you there was another flow out of the tricriticalizing model, and that preserves a different kind of symmetry, the Tambara-Yamagami symmetry. That one, there's 3 ground states at long distances, and there are 3 possible representations that you can write down of this symmetry. So here they are. So remember, each of these nodes is a ground state. These arrows, if they go from here to here, that's a particle over this vacuum. Going across, going between nodes, that are solitons. So these are the symmetries tell you that the states come in multiplets that look like this. It doesn't tell you a priori how many there are. And this flow was also solved by Samologikov, and he said that there is exactly one in that representation. Exactly one set of stable particles in that representation. So again, in his analysis, some of these degeneracies are just miracles. In ours, they're just kind of for free because of the multiplet structure. Okay, I'm going to do the last thing for Alexei. So integrable examples are fun to benchmark your analysis, but that's not, you know, it'd be better to say something new about a system that people care about. And so that's what I would like to do now. I'd like to tell you about some examples in 1+1D quantum chromodynamics. So I'll be kind of fast. So we're in two space-time dimensions. We're going to study gapped QCD in 2 space-time dimensions. So we're going to have a gauge theory with some gauge group G and massless fermions in a representation R. So that's a non-trivial RG flow. At short distances, it's just a bunch of free fermions. At long distances, it is believed that the solution to that theory is a coset model, coset theory. So some notation here. So this is the index of this representation. So to work out the levels of the coset, you need to do a little group theory. Now, I want to discuss the simplest situation where the infrared is gapped so that I could think about this theory as a model of particles, solitons, etc. I don't have to worry about any gapless soup in long distances. And you can work out, based on this infrared description, what the condition is for the infrared to have a mass gap. Right? So you just need to compute the central charge of this coset. And if you find that it is 0, that means that the infrared is gapped. Not trivial. There can be many vacua. There can be particles and solitons, as we'll discuss, but at least it's gapped. So we know particles and solitons and distinct finite vacua are the right language for thinking about that problem. Okay. So that's the situation we will be in. One interesting point here is that gapped QCD always has an interesting fusion category symmetry. Okay. Never the trivial symmetry, always some interesting fusion category to study. Okay, and I've written some discussion here using 2+1D Chern-Simons theory to tell you what this fusion category symmetry is. It's not super important, but this is how you work out a priori what the symmetry is given any particular set of fermions and gauge group. So that's a useful tool using 3D TQFTs. 5 minutes. Let's get to the punchline. Okay, let me do the simplest example. The simplest example of gapped QCD is SO3 gauge theory. The simplest interesting example is SO3 gauge theory with matter in a symmetric tensor, 5-dimensional representation. That's sort of the simplest place to illustrate these. So a single fermion in the 5. So what's the symmetry here? The symmetry has 3 simple lines. So there's the identity. There's some Z2 symmetry V. And then there's some non-invertible fellow that we call A. So you see, for instance, that A times A is a sum of a bunch of other things. That's this non-invertible fusion symmetry. It's not one that is very well studied. Doesn't have a fancy name as far as I'm aware. But it's the symmetry of this gauge theory. And in the infrared, this symmetry is spontaneously broken, leading to 3 vacua. So this gauge theory has 3 vacua at long distances. And here are the possible representations. There are 3 of them. So there's this one where each vacuum supports a lonely particle, but all of the same mass. There's this one where there's a soliton-anti-soliton pair for some reason between just these 2 and a lonely particle, all of the same mass. And then there's this more Baroque pattern. And again, a priori symmetry alone does not tell us how many of each multiplet exist. But if we remember that fact that I told you about at the very beginning, that the lowest energy soliton is stable, that has a generalization here. It tells you that each superselection sector of Hilbert space is non-empty. So you know that this representation has to appear. So at least these states exist. Okay. So I get a little more than just pure symmetry analysis here. I have told you about some soliton particle degeneracy in this QCD theory. That was not known before. And we can do that for other gauge groups and other matter content. It's kind of a turning the crank exercise now. Okay, so let me sum up here. What did I tell you? So non-invertible symmetries imply novel degeneracies in the massive spectra. That is the main punchline to take away. They can relate particles to solitons. That's something that can never be done by an invertible symmetry. There was some math, some heavy math in the middle. We had this key role played by module categories. That was this new algebraic structure that we needed if we wanted to do fusion category symmetry on manifolds with boundary, on intervals. And we have this interesting application, not just to integrable things or rational conformal field theories, which people have studied a lot, but to 2D gauge theories, one space, one time dimension gauge theories, where non-invertible symmetry gives us a new tool to think about finite number of color results, in which I'm very excited about. Okay, so obviously a future topic is lifting out of the 1D world and into the higher dimensional world. That project is ongoing. So thanks so much. Yeah.
So in supersymmetric gauge theories, if you study the parameter space, it is like often happens that you find points where particles become exactly degenerate with solitons. For example, electric charges with manifolds.
Mm-hmm.
So do people study if there is actually an invertible symmetry at this point?
Thank you very much for the question. So for yes, so for instance, the simplest example is like n equals 4, tau equals I.
Okay.
Yeah, that's the self-estimate point.
Theta equals pi.
S equals I.
Yeah.
G
okay.
equals 1 in some units, right?
Right.
But theta equals 0. So that indeed that you might think that electric magnetic duality becomes a symmetry of the theory at that point, and actually it is a non-invertible symmetry.
Okay, and yeah, but classical examples that I was thinking about obviously is more broad. Like in n=2 with fundamental matter, you can have plenty of such situations.
Yeah. So in general, I don't know if people have proved the theorem, but in general, in the examples that people investigated, it becomes a non-invertible symmetry.
Okay.
Yeah.
Two completely unrelated questions. First one, sort of a repeat of earlier questions. So if I take the tricriticalizing example and I add the Fibonacci preserving deformation, how do I think about the resulting phase in terms of the other global symmetries? Like, are other ones broken?
Other ones are explicitly broken by the deformation.
Okay, which ones?
Well,
I think I missed that.
Yeah. So I went kind of fast through it. So here, I mean, there's a condition that you need to, if you have a topological line L, which exists at the critical point, and you want to know, is it preserved by the relevant deformation? The condition you need to check is this, this is the quantum dimension of the line. This is something you could check with the S matrix. And so we have these two interesting relevant operators in the tricriticalizing model, and the total symmetry has these two simple subcategories, this Fibonacci and Tambari-Yamagami. And so each one of these preserves one of those categories, but explicitly breaks the other.
And the second question is a broad philosophical question, probably. So are there ever dualities which do not correspond to non-invertible symmetries?
You mean self-duality?
Yeah, self-dualities. But like Android duality, you.
I think it depends on how you interpret the word duality.
Okay.
Well, first of all, let me say that although I emphasized that a lot yesterday, especially in one spatial dimension, there are non-invertible symmetries that seem to not have any duality or self-duality interpretation. Like a general fusion, simple ones like Tambari-Yamagami do, but a general fusion category does not have such a simple interpretation.
Yeah. Does this Fibonacci one have?
Sort of. I mean, it's kind of degenerate. Yeah. I'll
talk about it.
Yeah. But more broadly, the question might hinge on what you interpret the word duality to mean. Do you interpret the word duality to mean the systems are exactly the same at all energy scales, or that they flow to each other?
Let's say in infrared.
Well, then the answer is probably no.
Okay.
Infrared dualities probably do not lead to new kinds of symmetries, even if they're self-dualities. They might lead to some structure, but not exact symmetries.
So if I hand you a system, say in 2+1D that has boson vortex symmetry in the infrared, you wouldn't say that has some associated.
Not in general, no.
Okay.
Yeah.
I wanted to understand a little better. I think a comment you had said to Jen about in the triplet in this Fibonacci system. I think you said the particle could decay to a soliton and an anti-soliton.
Yeah.
Well, so first off, these are all energy eigenstates?
These states that I'm talking about here are energy eigenstates, and they have the same energy.
Okay, so like they wouldn't actually, like if you dynamically evolve the system, they wouldn't decay because they're energy eigenstates.
Yeah, but I think he was asking about a particle over here. Why is there no particle on this vacuum?
Oh, I see.
Like that's somewhat surprising. There is no Z2 symmetry of this potential that I wrote, right? So in principle, there does not have to be any symmetry respecting swapping the two states. And in this representation, there is not, right? There is a finite energy stable excitation that goes from the right vacuum to itself, but there's no corresponding such excitation on the left.
Oh, okay.
And what I was saying is that you could try, in perturbation theory, if the model is weakly coupled, you might try to build such a thing. But at finite coupling, that state is not stable.
Okay, all right, yeah. So let's come back to my question about the rule of the coupling here.
Yeah.
Is it
So
lambda has
the
to
role
be-
of the lambda, so that lambda will blow. So okay, so I'm a little bit cheating is the answer. So this discussion rigorously applies to what happens when you start at the fixed point and deform out of the fixed point. Right? The potential gives you kind of a good way of visualizing what that is, what that will look like, especially the infrared and some aspects of the symmetry. But it only describes the model in some sense when the couplings are one.
Yes, I think some units of one is involved.
Yeah, exactly. So that's why it's not a computationally useful thing for finding this degeneracy.
So in this scenario, right? If I want to understand the dynamics of the system, is it a weakly coupled theory or strongly coupled theory? It's in fact the strongly coupled theory where both the particle interpretation and the soliton interpretation are both strongly coupled. There's no weak factor. Right?
That's right. Yeah. That's correct.
So that's why they're mapping to each other.
That's why they can map to each other. Indeed, the symmetry only exists coming out of the critical point. Yeah.
Any questions?
Clay, I have a question.
Yeah.
Can we go to the last page before conclusion?
Sure. And now somehow oops.
Yeah. Yeah, I just wonder, is there a simple physical interpretation of these particles? For example, in QCD theory, we know that we can say baryons, mesons, quarks, gluons. So can we have such a picture for these particles?
That's a great question. I can tell you what expectation values change. So I can tell you like the states that label the order parameters that label the distinct vacua. That I can do. I do not have like a kind of flux tube picture for all of the states yet, but it's something that we're kind of thinking about. But so far the level of knowledge is just I could tell you like what local operators labeled how to label different ground states using gauge theory language.
Okay, I see.